Hello and welcome to this second video lecture, part of our series of lectures designed to guide you through the BSc Level 1 curriculum. So if you've ever attended an echo course or picked up an echocardiography textbook, then almost without doubt that course or that textbook started with a chapter on the physics of ultrasound. Now of course it is completely possible for you to generate diagnostic images without fully understanding how those images are generated. But if you have a basic understanding of these principles, it will allow you to produce optimized images time and again, and it may help you recognize artifacts that lead to diagnostic uncertainty. So in this lecture we're going to talk about how ultrasound is used, how images are generated, what some of the drawbacks of using this technology can be. Okay, so we want to make an ultrasound image, so we're going to need to start by taking an ultrasound probe. And this is a phased array probe, the type we use for transthoracic adult echocardiography. And within the housing of this probe we've got a grid of piezoelectric crystals just below the footprint. Now the key feature of these piezoelectric crystals is that if you apply a charge to them, they will change shape, they will deform in a predictable fashion. So we can apply an alternating current, we can make the crystal get bigger and smaller, we can make it oscillate, and if the probe is held against our patient, then when we generate that kinetic energy, that energy will propagate through the patient in the form of a wave. Let's get a sense of how that's going to work in practice. So let's hold our probe against the patient's skin, and initially all of the particles in the patient, we can imagine those as being evenly spread apart. Now as we start to generate a wave of kinetic energy, we're going to push those particles. We're going to push some closer together, and because we can neither create nor destroy any particles, if we're going to push some closer together, then inevitably we're going to end up with areas where some of the particles are spread further apart than they were at rest. So those areas where we've pushed the particles close together, we're going to call those areas of compression, and areas where the particles have been spread apart, we're going to call those areas of rarefaction. Now if we freeze time, take a single moment in time, and have a look at what's happened to those particles. So as we move into our patient, we move from areas where the particles are at their resting pressure, to areas where they've been compressed, the pressure has been increased, to areas where there's been rarefaction, particles have been spread apart, the pressure has decreased, and back to the resting pressure. So if we plot this on a graph, we end up with a sinusoidal wave as demonstrated here, with distance on the x-axis and pressure on the y-axis. And if we measure the distance between an area of resting pressure through compression and rarefaction back to resting pressure again, then that distance is our wavelength. Conversely, rather than freezing time, we can allow time to run, and we can consider a single point in space, and watch as in that point of space the particles move together, pressure increases, and the particles spread apart, pressure decreases. And we can plot a similar wave on the graph, but now our x-axis is time, and once again our y-axis is pressure. And now the measurements along the x-axis, from an area of resting pressure through compression, rarefaction back to resting pressure, is one period. So another of the key characteristics of our wave is the propagation velocity, the speed at which the wave moves into our patient and then back towards our probe later on. So the speed at which the wave moves is dictated by the medium it's moving through. You can see in this table that the wave will move through different tissues within the body at different speeds. Now seeing as the ultrasound machine doesn't know which tissue the wave is moving through, and it assumes that the wave is travelling at a constant velocity of 1540 meters per second. The final characteristic of our wave that we need to describe is the frequency. The frequency describes the number of periods per second, or if you look at a single point in space, the number of times a wave travels through that point in space within 1 second. And this is measured in hertz. Human hearing can typically detect sounds that have a frequency of between 20 Hz and 20,000 Hz, whereas medical ultrasound uses frequencies many times greater than this. In adult echocardiography we typically use frequencies in the range of 1 to 8 MHz, 1 to 8 million Hz, or 1 to 8 million periods per second. The relationship between the different key characteristics of our sound wave can be described by the equation velocity equals frequency times wavelength. Okay, so let's consider some frequencies we might typically be using for adult echocardiography. So if we're assuming that our wave is travelling at 1540 meters per second, if we're creating a wave with a frequency of 4 million Hz, then that wavelength will be about 0.4 millimeters. If we halve our frequency, then we'll double our wavelength. So we'll halve our frequency to 2 million Hz, and that will increase our wavelength to approximately 0.8 millimeters. This is important because wavelength is one of the key determinants of our axial resolution, our resolution from the near field to the far field. Our ability to discriminate between two reflective surfaces relies on the fact that the structure that's reflecting our wave is larger than our wavelength. Simply put, smaller wavelengths are able to see with greater resolution. Okay, so now that we understand how we've generated a wave of kinetic energy, Let's now consider what happens to that wave once it passes into our patient. So what can happen to that wave? Well, some of the energy will be reflected straight back towards the probe. This is essential because the whole basis of using ultrasound to image the body relies on the fact we can reflect energy off structures within the body and detect it as it returns to us. Different tissues within the body have different levels of acoustic impedance, which is closely related to the density of the tissue. As ultrasound moves between two tissues with different levels of acoustic impedance, much of the energy passes on through, however some will be reflected back towards the probe. If you have a broad, smooth tissue interface, then we observe specular reflection. The tissue interface acts like a mirror and reflects the energy wave back towards the probe. The angle of reflection is influenced by the angle of incidence, the angle at which the sound wave strikes the tissue interface. So if you have a reflective structure that's perfectly perpendicular to your ultrasound beam, for an example, let's take the pericardium posterior to the left ventricle in the parasternal long axis view, and our ultrasound beam strikes this at 90 degrees, then the majority of the energy will be reflected back in the direction from which it came. If the tissue interface that our ultrasound beam is striking is not perpendicular to the direction of the ultrasound beam, then the majority of the reflected energy will be reflected away from our probe and a smaller proportion will make it back to our probe. For an example, let's consider the subcostal four-chamber view, and here it's unlikely that the intraventricular septum will be perfectly perpendicular to our ultrasound, and therefore less energy will be returned from the septum here than it would be, say, in a parasternal long axis view. The next interaction to consider is scattering. Scattering is a form of reflection that occurs when the ultrasound beam strikes a structure that is smaller than the wavelength of the transmitted beam. When scattering occurs, the energy is reflected in every direction, regardless of the angle of incidence. Far less energy is reflected than with specular reflection, and certainly the amount of energy that returns to a probe following scattering is many orders of magnitude less than occurs with specular reflection. And scattering is felt to be responsible for the speckled texture, the speckled appearance that you see within the myocardium when seen on ultrasound. The final interaction between the ultrasound wave and the body that's essential for us to understand is attenuation. Attenuation is the global term for the total amount of energy lost as the wave travels through the patient. So there are multiple ways in which the energy can be lost. The majority of it will be converted to heat in a process called absorption. Some of the energy will be reflected away from a probe, and a very small amount will be reflected back towards the probe. Another key concept to understand is that the rates of attenuation are related to wavelength. Waves of a higher frequency, and therefore a smaller wavelength, suffer attenuation at a faster rate. So if we choose to use a high transmitted frequency with a short wavelength, we're going to observe superior resolution, but the cost is that we get less penetration, as attenuation happens at a faster rate. In practical terms, if you're trying to image deep structures, say a depth of 20 centimeters, there's little point using a transmitted frequency in the range of 10 million Hz, as the attenuation will be so great that so little energy will return to the probe, such that you won't be able to produce a usable image. 2D images are typically generated using frequencies in a range of 4 to 7 million Hz, as we try to seek a optimal trade-off between resolution and penetration. So we've said that it's the returning wave that allows us to generate an ultrasound image. This is because the piezoelectric effect can work in reverse. Applying kinetic energy to the array of crystals generates a charge that travels back into the ultrasound machine and can be interpreted by the ultrasound software. So what information does the ultrasound software record? Well, it measures the amplitude of a returning wave, how much energy returns, and it also measures the amount of time it took for the energy to return following the transmission of the original wave. So the piezoelectric crystals are only transmitting energy for a tiny fraction of the total cycle time. For the remainder of the time they're listening. They're waiting to be struck by returning kinetic energy, convert that into an electrical signal and send it to the ultrasound machine to be interpreted. Let's imagine that our ultrasound wave is striking a reflective surface 10 centimeters from our ultrasound probe. So that energy will have to travel for 65 microseconds to travel the 10 centimeters into the patient and strike the reflective surface, and then travel back another 10 centimeters, taking a second 65 microseconds to return to the probe. So by knowing how long it took for the energy to return to the probe, the software can estimate how far away the reflective surface must have been. In addition, the ultrasound software also recognises the amplitude of a returning wave, the amount of energy that returns to us, and that amplitude is converted to a brightness value on a grey scale. So that's going to give us information in one dimension, but now we're going to convert that into a two-dimensional image. So to generate our 2D image, we're going to create multiple one-dimensional lines of information that fan out from our probe. These scan lines, which fan out from a probe, run not quite parallel to each other, such that they're closer together in the near field and spaced further apart in the far field. The ultrasound software then uses an averaging process to fill in the gaps between the lines. So you can see how having a greater number of lines will increase your resolution, as there will be less requirement for the averaging process to fill in the gaps. The time taken to generate a single two-dimensional image will depend on the size of sector that you've chosen, and how many lines you wish to use to build up that image, the line density. So let's consider this example. Here our sector depth is set to 20 centimeters. Therefore a single line requires 260 microseconds. That's 130 microseconds to travel 20 centimeters in, and another 130 microseconds to travel 20 centimeters back to the probe. If the ultrasound software decides to build up this image out of a total of 128 lines, then it's going to take just over 33 milliseconds to produce each of those 128 lines. We can do this a total of about 30 times per second, and so our frame rate, or our temporal resolution, is 30 Hz. So we're going to sweep lines from one side of our sector all the way around to the other side of the sector, and then we've filled that sector with lines. We're going to average the gaps in between, create a single two-dimensional image, and then we're going to start that whole process all over again in order to create the next frame in our sequence. So when we're generating an ultrasound image, we're bound by the laws of physics. Sound waves move relatively slowly, and so it's impossible to have a large sector with a high frame rate and a high line density. And when we're generating our images, we're constantly playing these factors off against each other, trying to find a compromise that shows us the image that we need. Alright, let's take a look at an example. Let's imagine that we're generating an image with a sector angle of 60 degrees. Now if we decide to increase our sector angle up to say 120 degrees, then if we want to maintain the same frame rate, then each of those lines will be spread further apart, decreasing our line density. If we want to maintain the same resolution, maintain the same line density, then drawing those extra lines will take additional time and decrease our frame rate. When using modern ultrasound systems, you'll be asked to specify the depth to image and the sector angle, and the ultrasound software will then produce a balanced image, balancing frame rate and line density. Higher end systems will allow you to choose between an image that favours frame rate or resolution. Okay, so this nicely leads us on to think about which of the settings on the ultrasound machine a level 1 sonographer needs to be able to master in order to produce optimised images. So let's start with sector size. So we're going to set our sector depth and we're going to set our sector angle. So this is a parasternal long axis view, and here you can see that the sector depth is set to 24 centimeters and the sector angle looks like it's around about 90 degrees. So we're asking the ultrasound machine to image a very large part of the body. Now if the area that we're interested in is the heart, then the bottom half of the image and the right hand third of the image aren't providing us any useful information. We're spending time sending ultrasound waves to parts of the body which aren't giving us any useful information back. So with the ultrasound system set up as it is, we've got a frame rate of 37 frames per second, 37 Hz, and you can see that information displayed in the top left hand corner. Now that's a reasonable frame rate, but given this patient is tachycardic, that's not leaving many frames per cardiac cycle. In addition, our lateral resolution is going to suffer because our line density won't be that high. Alright, so let's try again getting our parasternal long axis. So this time we've made our sector much smaller. We've decreased our depth to 12 centimeters, we've decreased the angle of the sector to probably about 50 degrees, and we're imaging a much smaller part of the body. Now our frame rate has shot up to 94 frames per second. But this view is inadequate because we're losing a lot of detail that's important to us. The aortic valve and the aortic root are disappearing out of the right hand side of the image, and we can barely see the posterior aspect of the left atrium. And there may well be a pericardial effusion that we're missing because we just haven't made our sector deep enough. This third attempt at the parasternal long axis view probably strikes the balance just right. Now all of the areas of interest are displayed, but we're not wasting any space and therefore wasting any time imaging areas that aren't useful to us. In this image our depth is set to 14 centimeters, our sector angle is probably around about 70 degrees, and we have a frame rate of 64 frames per second, with a reasonable line density producing a reasonable lateral resolution. Okay, so as I mentioned earlier on, some ultrasound systems, especially higher end systems, will allow you to specify whether you'd like an image that favours frame rate or favours lateral resolution. So here you can see two images side by side, both parasternal long axis of the same patient. The image on the left is produced using an increased line density, and the frame rate is just 39 frames per second. For the image on the right, we've asked the ultrasound software to favour temporal resolution, increase the frame rate, but it's done this at the expense of reducing the number of lines. There's no single correct way of setting up your system here, and the decisions you make about trading line density and frame rate will be dictated by what it is that you're trying to demonstrate. In addition, the ultrasound software may allow you to adjust the frequency of a transmitted wave. So here we've got two images, both with the same sector size and the same line density, but the image on the left has been produced using a low frequency ultrasound wave that favours penetration, whereas the image on the right has been generated using a high frequency wave, which favours resolution in the near field, but suffers when trying to image the far field. Once again, neither of these decisions is right or wrong, and if you can adjust the frequency of a transmitted wave, then your decision to do so will be influenced by what it is you're trying to demonstrate. Alright, next up we need to consider focusing. So to understand focusing, we have to think about the shape of a wave as it leaves the transducer and passes into the patient's body. We need to think about which particles within the patient's body are going to be disrupted and which aren't. So this is a 2D representation of a 3D concept, and so we need to use our imaginations a little bit in order to imagine this in 3D. So as the ultrasound wave first leaves the transducer, it initially behaves like a column. So all of the particles within that column will experience alternating compression and rarefaction. After a few centimetres, the beam starts to diverge, and you can see that demonstrated here as an ultrasound beam that's initially got parallel sides, and then the sides start to diverge and you end up with a greater area of disruption in the far field than in the near field. Now of course this would only be the shape of our ultrasound beam if we were using a transducer with a single crystal, but as we know our phased array probe has got a grid of crystals, and so we get areas of overlapping ultrasound beam that look a little like this. So the shape of the ultrasound beam you can see demonstrated now is the shape of disruption that you would see if a piezoelectric crystal grid was completely flat. But we can alter the shape of the beam by introducing an element of concavity to the piezoelectric crystal grid. Alternatively, we can place an acoustic lens in front of the grid, which produces the same effect. The best way to understand this is to see it happening in action, so let's start introducing an element of concavity into our crystal grid, and you can see that as we bring those ultrasound beams generated by the ultrasound crystals at the extreme end of the grid towards the centre, we start to get overlapping beams, where the area of overlap is greatest in the far field. What happens if we use our acoustic lens to bring those ultrasound beams in even further? Well, then we get the area of maximum overlap happening closer and closer to the ultrasound probe. Our focus point moves closer to the transducer as we angle our ultrasound beams towards the centre to an ever greater amount. If there's an area of the image or a particular structure that's of particular relevance to you, then you can adjust the focus point such that the beams converge around that area, producing the greatest degree of resolution at that point. If there's no one structure or one area that's of interest but you want a balanced image, then you should probably place a focus point around about the midway point of the depth scale. Alright, let's have a look at the practical effects of adjusting the focus point. So here we've got two parasternal long axis images, and the only thing I've changed is where the focus point is positioned. So for the image on the left we have a focus point in the extreme near field, and the image on the right the focus point is on the extreme far field. And just take a second to have a look at how those two images are displayed differently. Now unless we're specifically interested in something in the extreme near or far field, then we're probably going to want to produce a balanced image here. And so for the apical 4-chamber view I like to set my focus point around about the level of the basal third of the left ventricle. And here you can see that the area highlighted in green is the area with the greatest resolution. But having said that, there's still pretty good resolution throughout the entire image. The next setting that the sonographer needs to consider is gain. Gain refers to the degree of amplification of a returning signal, and the purpose of adjusting the gain is to produce a balanced image which utilises all of the grayscale. When the gain is set too high and the returning signal is over-amplified, as it is here on the left, then the image will appear too bright. By contrast, if the image is undergained, as we see on the right, then the whole picture appears too dark. Both over and undergaining images can cause important details to be lost. This is analogous to either over or underexposing a photograph, where overexposure will cause details to be blown out in the highlights, and underexposure will cause details to be lost within the shadows. The gain should be set such that we take advantage of the entire grayscale. An ideally balanced image will have simple fluids such as blood appearing as black, whereas highly reflective structures such as metal and dense calcium will appear bright white. All other structures should be represented as a shade of grey. Now we know that due to attenuation, the amount of energy that ever reaches the far field is many orders of magnitude less than the amount of energy that reaches the near field, and that returning signal from the far field needs to be amplified to a much greater degree in order to produce an even image. The process by which the ultrasound software adjusts the degree of amplification due to how late the signal returns is called time gain compensation. Now sometimes when we see the image displayed on our screen, we're not entirely happy with how the ultrasound software has tried to produce a balanced image. We might have areas within that image that appear too bright and other areas which appear too dark. Let's take this image as an example. Here the near field is darker than we would like it to be, and there's a band of excessive brightness about 3/4 of the way down the image. So when we have this situation, we can manually override how the image is displayed using the time gain compensation controls. Typically these will be either physical sliders, or if you're using a system with a touchscreen, there'll be sliders on the touchscreen. The controls are then slid to the left or right in order to increase or decrease the brightness of a particular region within the image. Alright, now let's put all of that together and consider all of the controls that the level 1 sonographer needs to master to produce optimized images. So first of all, you're going to think about your sector size. How deep do you need to image? What's the ideal sector angle? Remember, include all of the structures that are of interest to you, but don't include anything else. What about line density? How many lines do you want to make up to draw each individual image? The greater number of lines you use to produce one image, the fewer images you'll be able to have, but the greater resolution they'll be. Does your machine allow you to adjust the frequency of a transmitted wave? If it does, is penetration important to you? Do you need to see those far field structures best? Remember, doing so, selecting a longer wavelength will decrease your axial resolution. Where should your focus point be? Is there a particular structure or pathology of particular interest? If there is, put the focus point over that area. If there's not, place it somewhere around about the middle of the image. And have you got the gain right? Do you have a nice balanced image where everything is easily seen? Blood is black, metal and calcium are white, and everything else is sitting on that grey scale. Of course, it isn't always possible to produce a perfect image, especially in the sort of patients that are being investigated with a level 1 scan. But if you're able to produce the best image possible in the circumstances, then you've got a greater chance of getting the diagnosis right. Alright, so next up we need to consider artifacts. So artifacts occur when the ultrasound software incorrectly displays something as present when it isn't, or fails to demonstrate a structure when it is present, or demonstrates a real structure but in the wrong location. Now there are some commonly occurring patterns of artifacts, and if we know what these are, and we can anticipate them and recognise them when they do occur, then it reduces our risk of getting tricked. Alright, so let's have a look at some of these artifacts and the ultrasound physics behind them. So first of all, let's consider acoustic shadowing. So acoustic shadowing occurs when you're trying to image through a structure that's so reflective that none of the ultrasound energy passes through it and all is reflected back towards the probe. A common example of this is trying to image through a rib. You place the ultrasound probe on the patient's chest and you see an area of shadow or dropout beyond a very bright structure and you can't see anything behind it. Another example is when the patient has prosthetic material within their heart. So for example, a prosthetic heart valve or a metallic heart valve will cause dropout beyond the reflective surface. So let's have a look at this example. This is a parasternal long axis view and you can see this patient has a prosthetic mitral valve replacement in the mitral valve position. And in the far field, so beyond the valve, in the posterior wall of the left atrium and beyond, you can see these dark shadows highlighted by the arrows, but are dropouts caused by acoustic shadowing. So if acoustic shadowing is an example of an artifact which causes us to lose part of our image, let's now consider a couple of examples whereby the ultrasound software demonstrates images erroneously, shows us structures which aren't really present. Okay, so the first of the examples to consider is refraction. Refraction occurs when the ultrasound beam deviates from its normal path as it passes through the tissues. Its path gets bent, in much the way that a beam of light gets bent as it passes through a glass of water. Now if that ultrasound beam then strikes a structure that reflects the energy back to the probe, then the ultrasound software very reasonably but incorrectly imagines that that reflective surface must have lain along the original path of the beam. So what does this look like in practice? Well, this is a parasternal short axis view showing a very common example of a refraction artifact. So here you can see the aortic valve annulus, and displayed to the left of the annulus you can see a fainter version of a true structure, almost like a ghost of the aortic valve. A second example of when an artifact can cause an image to be displayed on the screen when the structure is not really there is caused by a phenomenon called range ambiguity. Range ambiguity is the reason why we sometimes see a mirror image displayed behind a highly reflective surface. So getting your head around why range ambiguity occurs can be a little bit challenging, so let's consider an example, talk through it with some numbers and see if we can make it make sense. So let's imagine that we're imaging our patient and these two grey structures here represent reflective surfaces within the patient. The first is 10 cm from a probe, and the second is 12 cm from a probe. So we start firing our ultrasound waves into the patient, and the first wave that reflects off the first line travels 10 cm into the patient, 10 cm back to the probe, and has travelled a total of 20 cm. So when the ultrasound software displays this on our screen as a structure, it estimates that this structure must be 10 cm away from us. Now, any energy that passes through the first line and is reflected off the second line will travel 12 cm to the second line, 12 cm back to the probe, total distance travelled 24 cm, displayed on our screen as a structure 12 cm away. So far, so simple. Now, what happens if we have energy that passes through the first line, is reflected from the second line, comes back up and hits the underside of the first line, is reflected back down to the second line, and then is reflected off the second line back into the probe. That energy has then travelled 12 cm to the second line, 2 cm up to the first line, 2 cm back down to the second line, and 12 cm back to the probe. Total distance travelled 28 cm, and therefore the ultrasound software displays a structure, a mirror of the first line, 14 cm from the probe. It shows the first line being exactly as far away from the second line, but now in the far field rather than the near field. Alright, so what practical examples of this do we commonly see? Well, in reality it's large specular reflectors that are perpendicular to our ultrasound beam that produce this effect. And we commonly see it when the specular reflector is the pericardium in the parasternal long axis view, or the diaphragm when we're imaging the lung bases. So let's consider this example. So this is a parasternal long axis view, and your eye is probably drawn straight away to the large vegetation on the mitral valve. If we look beyond the infralateral wall of the left ventricle, we can see that there's a moderate-sized pericardial effusion. And then beyond that there appears to be a second effusion, which we might initially be forgiven for thinking as a pleural effusion. However, within this deep effusion we have a structure that's moving with the same frequency as the heart. And actually what we're seeing is a reflection of the infralateral wall of the left ventricle, and that second effusion isn't a pleural effusion, but is actually a reflection of a pericardial effusion. Now this is by no means an exhaustive list of the artefacts that you may see, but it just introduces the concept of artefacts, and I think if you understand how the physics of ultrasound leads to artefacts being generated, it gives you a better chance of spotting them when they occur, and potentially reduces your risk of making incorrect diagnoses. Okay, so far we've mostly been considering the generation of two-dimensional images, sometimes referred to as B mode or brightness mode. But there's another important mode of imaging that the level 1 sonographer needs to master, and that's M mode or motion mode. So M mode involves choosing a single line on our 2D sector, and then sampling that same line repeatedly many times a second, up to about 2000 times per second. We then use that information to produce a graph, whereby time is on the x-axis and depth is displayed on the y-axis. So in this example here we start with a parasternal long axis view, and we place our cursor just beyond the tips of the mitral valve leaflets. And you can see here that as our cursor moves from the near field to the far field, it passes through first the interventricular septum, then the LV cavity, and then the infralateral wall. We then sample along that line throughout the entire cardiac cycle, and repeatedly through several cardiac cycles, and produce a graph as you can see on the right hand side of the image now, where the near field is displayed at the top of the image, and the far field at the bottom of the image. So you can see on our graph about 1/3 of the way down we have the interventricular septum, and then right at the bottom of the graph we've got the infralateral wall, historically termed the posterior wall, and beyond that the right pericardium. There are lots of practical examples where M mode can be of use to us, and we're going to cover some of these in subsequent lectures. Alright, so that's it. That's our brief introduction to the physics of ultrasound, and how we can use it to create two-dimensional images of the moving heart. I think we'll finish by summarising some of the key things we've discussed during this lecture. So first of all, the piezoelectric effect is key. This is how we're able to convert electrical energy into kinetic energy that we can send into our patient, and how we're able to convert that returning kinetic energy back into electrical energy that we can detect. The ultrasound beam that we pass into our patients behaves like a wave, and the key properties of that wave are its velocity, its frequency, and its wavelength, and these properties are linked intrinsically. Most of the energy that we send into our patients is lost, it never comes back to our probe, with the vast majority being converted to heat. But when that energy does come back to our probe, we can measure how long it took to get back to us and how much of it returns, and use that to start building up a picture. We can build up 2D pictures by sweeping multiple lines of information across from our phased array probe, and then using these multiple lines to build up a single two-dimensional image, and then by producing multiple two-dimensional images within 1 second, we can create a moving image. When we're building up our 2D images, we're constantly having to compromise between the size of the imaging sector, the number of images we can produce in a second, and the resolution of those images. And as sonographers, we need to make decisions about which compromises we're prepared to make, and that's going to be dictated by what it is that we're trying to demonstrate. And we now know that artifacts can occur, that the ultrasound software can produce images that are misleading, and we understand why they're misleading and how to spot this when it's happening. Well, I hope this lecture's been helpful, and in the next lecture we're going to have a look at ventricular size and function. How can we use these 2D images that we've just learnt how to generate to look at the size of a heart and how well it's working in our sick patient.